Our presenter today is Daniel Carreno, Megger's Applications Engineer. Daniel is based out of Dallas, Texas. Thank you for joining us, Daniel.
Good morning, everyone. Thank you for joining us today. We hope that you will find this webinar useful. We're going to talk about why it's important to measure load resistance and in which situation makes sense to take these measurements. We will also cover what factors you should consider when choosing an instrument to measure load resistance and what are the best practices when doing this test. Well, and jumping right on topic, I would like to start answering the question, what is a load resistance measurement? Whenever we are measuring resistance values below 1 ohm, we consider those as low resistance, and we should be aware that at those very low levels, we are going to face a few challenges, like the influence of the test lead resistance. Also, if the poor test lead contact, and if we have a different joint between different metals, then we will have thermal EMS developed in the junction. So those are some of the challenges that we will face when making these measurements. So now that we know what a load resistance measurement is, you are maybe wondering, why should I measure this? If we recall from Ohm's law, we know that for a specified energy source operating either AC or DC voltage, the amount of current drawn will depend upon the resistance of the circuit or component. Identifying those resistance elements that maybe have increased above any acceptable value will help us prevent long-term damage to our equipment, minimize energy wasted as heat, and ultimately will help us ensure maximum efficiency of electrical components. Some of the problems that we can detect are degradation between contacts, for example, in a circuit breaker or a disconnect switch, excessive vibration in motors, for example. In the straps of a battery system, we can detect chemical corrosion or loss of torque in connections, for example, in bus bars, in substations. Of course, we should note that these problems that I just mentioned are not limited to the applications that I just said, and in most of the cases, we can have a combination of them in our application. Now, let's talk about a little bit more about those applications. Take motors, for example. We don't want to have adjacent coils having shorts between them or open circuits. So we can use load resistance testing to look for those conditions. And additionally, when we trend the resistance values we get with those states over time, we can identify the effects of overheating in our motor or generator. Now, take, for example, a pretty easy example. If we have a reel of insulated copper wire, it may have a tag indicating the wire gauge and the resistance per unit of length, or let's say the tag has been removed. We can just cut a small piece of cable, measure its resistance, and now when we measure the whole coil, we have a factor to calculate the total length of the wire we have on that drum. In industries that consume vast amount of electrical power, load resistance testing is a must. Let's say, for example, we have a bus in a substation and it's carrying 12,000 amps of current. If our bus has a resistance of 1 micro ohm, for example, the power dissipated in that bus will be only 144 watts. But let's say we have a problem in one of the junctions in that bus bar, and the resistance changes to 100 microohms. One may think that change is not a significant one, but at that level of current, if we calculate the power dissipated in that case, it will go up to 14,400 watts. So high resistance not only causes unwanted heating, but it will lead to energy losses, which increase operating costs. Or in other words, we will be paying for energy that we are not actually consuming or using a good use of. In the aircraft assembly industry, for example, a ground plane is a uniform path for static electricity to be discharged, and that will reduce the chance of damages to a lightning strike situation. So we can tell the importance of these system planes. This ground plane is provided by uniform physical bonds in the main mechanical structure and also in the main electrical frame of the plane. So when testing these connections, the lowest resistance values will improve the performance of such systems. Now, take a different example, the railway system. The bonds between the rails are part of the control system that tells the operator the location of different trains. So in systems, the third rail is the active source of power for the engine. So you can tell the importance of maintaining a high quality connection between the rails. When making measurements, the operator can select a 5-foot section of a track without a bond, make a measurement, and then repeat the same procedure, but now taking another 5-foot section of the track with a bond in the middle. So a rule of thumb in this case will be that those two values should be within a few microns. Usually, they should be different from each other, plus minus 5%. Now think of any metal joint that has to be welded. If we measure the resistance along the weld seam, we can determine its uniformity, as all the resistance readings should remain within a narrow band of values. Now, for this case, I should mention the operator needs to make the measurements with a fixture to keep the distance between the probes in a fixed relationship. It's very important in this case. Now, for example, this is a very interesting application on battery systems, on UPS systems. The battery cells are linked to each other with conductor bars called straps. These bars are subject to vibration, changing temperature due to the charging and discharging processes of the battery, and also, of course, to chemical corrosion. If only one of those straps in the system fails, then our whole bank will fail. So it's really, really important to prevent those conditions to happen, to be sure that we have a nice, healthy systems, and that those connections are quality connections, and the best and quickest way to assess that is measuring the resistance between the adjacent posts of battery terminals. Now, in the present, it's not unfamiliar to see solar or wind farms. In wind turbines, for example, it is essential to have a stable ground path from wind tips all the way to the base of the structure. This is really important, again, for the health of the system. And on this case, we will use a special set of leads that are longer than usual. So now that we have a better idea of the wide range of applications for low resistance testing, I think it makes sense for us to ask, how do I choose the right instrument for my specific application? There are several factors to consider when choosing a tester. We can pin them down asking ourselves a few simple questions. The first one would be, what are the resistance values that I expect to measure? Let's say if I want to measure the windings resistance of transformers, for example, I know I will have readings in the range of milliohms, but what if I want to measure the resistance of circuit breakers contacts? Then I know I will have readings in the range of microohms. So it is important to know what I'm going to be testing in order to select the right range of my instrument. This factor is closely related to resolution, which will define the sensitivity of my measurements. And if I want to trend my results, then I will want my instrument to have a good resolution, so I can do my trending in the correct way. The resolution also will play a big role on repeatability, which is also, of course, needed for trending my measurements. Now, the accuracy of my tester, it's important, of course, to have the right readings when I'm testing. And on this case, our instrument will have two different statements on the instrument. The ones that will state its accuracy in the percentage of the range, and the ones that will state the accuracy in the percentage of the reading. On this case, make sure you pay attention on this factor, and you should prefer the instrument that will state the accuracy in the percentage of the reading and not the ones stating the accuracy in the percentage of the range, as those will be less accurate. We also need to choose the right test current, the right range of current output for our tester. This will depend on several factors. The first one will be the rating of the equipment we're going to measure, the resistance range, and even the environment. We'll have to take into account the environment in which we will be doing the testing. If we have to do the testing in a substation, in a very noisy substation, then we'll need a higher current tester. And finally, the last factor to consider will be the measurement modes. And those will come into picture for applications like circuit breakers, for example. We see this in the circuit where it is recommended to run the current to avoid magnetizing the CTs. So even though when all that I just said sounds a little bit overwhelming, there are some common applications for example, 10 amps micro-ohmmeters, which are really common in the industry. This is again a common range that is used for several applications, like the one showed here in this slide. For example, the fast connections in battery systems, quality control and resistive components, and general conductor bondings. We have another common range of micro-ohmmeters that those are in the hundreds of the currents, and we will see instruments going from 100 amps all the way up to 600 amps. Among their applications, we will have contact resistance in circuit breakers, and to take these measurements, we have to use a minimum of 50 amps according to IEC 62271-100, and a minimum up to 100 amps according to ANSI C 3709. Again, those current values are the minimum values, and we can go up to the rated current of the circuit breaker. Now, we were talking about measurement modes. When we are making a resistance measurement, it is important that we understand how the instrument is injecting the test current in what we are testing. Some instruments will let the user decide what test mode to use, and some others won't let the user choose. But it's still very important that we know which test mode we are using, as for certain applications, using the wrong mode will yield in having unwanted results. Normal mode will inject the current in both directions, and I would say this is for modern micrometers. As in the past, the instruments will inject the current in only one direction. But again, in the modern meters, the normal mode will inject the current in both directions only for a given period of time. It will take those two readings, and it will take the average and show that to the user. The automatic mode is used in conjunction with spring-loaded leads that will sense a closed loop to automatically take the reading, and this mode also will inject the current in both directions, and it is particularly useful when making multiple quick measurements, like when testing strap resistance in a battery system. The continuous mode will apply the current in one direction only until the operator manually stops the test or the instrument will sense that the circuit is broken. This is useful, for example, when testing temperature rise in a motor, and we will need to take measurements for several minutes continuously. The unidirectional mode will apply the current in one direction only, as the name implies, and it is used when testing inductive specimens like motors and transformers. The round mode is not very common to see on the instrument, but it is implemented for some special applications like circuit breakers with CTs involved in the circuit. And this mode, what it will do is it will ramp up the current slowly up to the configured value, hold that current for a given period of time to take the measurements, and slowly ramp down the current. This is done to avoid magnetizing the CTs in the circuit breaker and modify their performance when putting those back in service. And finally, we should be aware that there are some special applications for low resistance tests, like transformers. And this is very important to know that for a transformer, we will need a special instrument with enough power to magnetize the windings, and it also should be able to discharge those windings after finishing the test for safety concerns, and also that instrument should be able to demagnetize the transformer when finishing all the testing, and that is to avoid leaving the transformer with residual magnetism and avoid damage when putting the transformer back in service. So now that we know the factors that we should consider to choose the tester for our application, let's talk about measurement modes. And I wanted to start this section with this.
Before we move on, can we answer a couple of questions from the audience?
Sure.
Can you explain a little bit more about why you have to demagnetize the transformer after testing winding resistance?
Oh, okay, good. That's a good question. Like I said, if we do the winding resistance on the transformer. And we know that we do that with DC current. So that will magnetize the core of the transformer. And if we don't demagnetize the transformer, then when we put it back in service, because of that residual magnetism, the first inrush current when we energize the transformer will be huge, and that of course will make us damage to the core of the transformer.
And in a busbar system, how can you figure out the range that you need? Is there any formula to use?
I'm not sure I understand the question.
No problem. Then we'll take it offline.
On Twitter and you contact him after we finish?
Yep.
Okay. Okay, continuing with the measurement nodes. These two that you have, I wanted to start this section with these two measurement methods that you have on your screen. The 2-wire and 3-wire methods, they are not meant for making low resistance measurements. But I wanted you to have this in mind so you can identify them, and in any day you see a tester with either 2 wires or 3 wires, you will know that those testers are not meant to taking low resistance measurements. The 2-wire method is used for readings above 10 ohms and up to 1 to 10 mega ohms, and the 3-wire is used for very high resistance values above 10 mega ohms, and this is the method that is typically used for insulation resistance. Okay, so now that we have these two in mind, that we know that those are not meant for low resistance testing, let's talk about the 4-wire method, the one that we will use for low resistance. We include the 4-wire because it will help eliminate the errors due to the contact resistance, and of course is the most accurate when measuring those low ranges of resistance. But how does it work? Let's look at the picture you have on your right. It shows a simple diagram of the basic components of a low resistance ohmmeter. We will have a constant current DC source and a DC voltmeter. Those two are individually connected to a measuring circuit, as you can see in the diagram. So we already said we use 4 test leads, right? We have the first 2, the current probes or the current leads, which we will connect to the DC source of our ohmmeter and to the test specimen. Then we will have the 2 potential leads connected directly to the DC voltmeter, and what it will happen is the instrument will inject the current, and then it will measure the voltage drop between the potential leads, and then that way the ohmmeter will know in the circuit. And as you can see in the diagram, the DC voltmeter won't include the small voltage that we will have on the current connections to the specimen. Another important consideration is being aware of if our application should be tested using either direct current or alternate current. If we use DC, we will be measuring the pure resistive component of the circuit under test. This type of instrument is the one used in most of the low resistance applications, except the ones where we need to measure the impedance of the circuit. So in that case, an AC instrument should be used to include both the resistance and the reactance of the circuit. This type of AC test is used to measure the impedance of battery cells, for example. Now let's talk about some of the recommendations for proper load resistance testing. First, when choosing the current we're going to use to take our measurements, we should always try to select the maximum or the highest current available based on the rate of the equipment we're testing, and also, very important, we should take extra care to ensure the test current would not cause an increase in temperature of the conductor under test, because that change in temperature will influence the resistance measurement we are trying to do. Now, another good testing practice is choosing the right test leads for our application. There are mainly three types of leads. The first one is the one with both the current and potential leads in one probe, as you can see in the left of this diagram. The second type is the one in which all four connections are separated. And the third one is a very common configuration. It's really easy to use, as it will have both the current and the potential leads combined in one connection. Both the current and potential points are placed 180 degrees apart from each other. Here in this picture, you will see four of the most common test leads for micro ohm meters. The two in the bottom are commonly used for battery testing, and the ones in the top, both considered Kelvin type because they have both the potential and the current connections in one spot. And these are typically used for larger conductors, like, for example, in transformers and circuit breakers. Now, the Kelvin type leads are, like I said, really common in the industry, because another important consideration when we are making our measurements is how we place our leads when we connect those to the specimen we want to test. As you can see in this slide, we should either put the potential probe inside the current probe, or at least in line with the current probe, and never connecting the potential probe directly to the current lead, because that will include that small voltage drop on the connection between the current probe and the conductor we are testing. There are even more rigorous tests in which we have to separate the leads, the potential leads, away from the current leads. And according to ASTM B19365, the potential leads should be separated from the current leads at least 1.5 times the circumference of the conductor under test. This is to make the measurements in the conductor zone that we will have the current flow uniformly distributed. Once again, for transformer, it is very important to make the measurements with the proper instrument, which should be capable of magnetizing the windings, and that is to be able to get a stable resistance reading. Also, for safety, the instrument should be capable of discharging the windings and perform a demagnetization, as we already talked about. On the current selection, really important, according to IEEE C57-152, we should not exceed 15% of the rated current of the winding under test. And again, that is to avoid heating of the conductor and changing the resistance of the winding. And finally, for the same reasons, the results should be corrected to a base temperature to be able to trend or compare to previous testing. For circuit breakers, the current selection should be made according to either IEC 62271-100 or NCC 3709, and that is for the IEC standard. They recommend a minimum of 50 amps all the way up to the rated current of the breaker, or a minimum 100 amps according to ANSI C37. And again, the best instrument for this application is one that will ramp up the current, hold it, and then ramp it down. For batteries, I will mention that this is the only application in which is allowed to take the measurements on a live or hot circuit, on an energized circuit. It's just that the operator should be aware of the flow current of the system. Now, I've been telling you several times already that in most of the applications, for you to know if the readings you are getting are correct, you need to compare those to either previous results or to manufacturer references. But what if you don't have those? Then in some cases, you can calculate the expected resistance value of a conductor if you know its resistivity. Using this simple formula, you multiply the resistivity of the material you are testing to the ratio of the distance between the two points of the material and the cross-section area of that conductor. And now I want to make a big emphasis on this consideration. The effects of temperature. All of our resistance readings are highly temperature dependent. As you can see in this graph, if you look at the copper curve, for example, you will see that the resistance will change about 40% for 100 degrees change in temperature. The recommendation is either measure the resistance at the same temperature of our reference values, or correct those measurements to a base temperature. When testing in the field, it is actually impractical to try to measure the resistance at the same temperature of our reference values. So what we will do is take the measurements at any temperature, but take note of that temperature and then use this formula on your screen to correct those values to a base temperature. In this formula, the R2 is the measured resistance, the T2 is the temperature at which you measure the resistance values, and T1 is the temperature at which you want to correct the values. Then A is the temperature coefficient, and that is dependent on the material of the conductor you are testing. In most of the electrical application, of course, we use either aluminum or copper. For the aluminum, you have a coefficient of 0.0038 per each degree C, and for copper, it will be 0.00393. So now that we have all